All right, so for electric potential lesson, recall from mechanics that when and only when the forces in a system are conservative, mechanical energy, I should say mechanical, except I can't spell today, mechanical energy is conserved. So mechanical energy is it's just the movement energies or the ability to move energies. So we're talking about potential energy plus kinetic energy. That's what we mean by mechanical energy. There are other types of energy, right? There's thermal energy and others, which really are all kinetic in disguise. Um, but I'm talking not about temperature type stuff. I'm talking about ability to move and energy of movement. Okay, so when an object loses kinetic energy, then it's going to automatically gain the same amount of potential energy and vice versa. So you guys know that when you take the initial kinetic energy and you add the initial uh, potential energy, that's going to give you the same sum as adding the final kinetic energies and potential energies. Now, when this happens, we call that a conservative system or a conservative force. When we talk about the forces, we say conservative usually, and when we talk about the system, we usually say that potential energy is conserved within that system. So the wording's not as important to me, but this means that whenever a conservative force is acting on a system, we can define a potential energy. Potential energy is not easy to define unless your forces are actually conservative. This is why you've never seen a problem that involves friction and potential energy in the same question. Friction is a dissipative force. You literally lose energy to heat, sound, and light. So because friction is non-conserving, we typically don't use potential energy while discussing it. There are exceptions and there's ways around it, but you hear the word potential energy associated with things like springs and things like gravity and electrostatical force. So potential energy refers usually to a conservative system. Now, it has been experimentally confirmed that the electric force is conservative. We don't believe we lose energy anywhere. So we can define the electric potential energy as, and this is just an old formula from your classical mechanics sections, okay? The potential energy is always the negative antiderivative of force dot displacement. Okay, this comes from the old idea that if you take force times distance or displacement, you get work, right? And work is the opposite of potential energy, because when you provide work, like squishing a spring, you just upped the kinetic energy. But actually, the spring's working on you. So what's happening is you're squishing the spring, right? And all this potential energy is getting stored, but actually the force that you're applying and the displacement you're getting are in the same direction. So you're providing positive work, but the spring's providing negative work. So according to the spring, the potential energy here is negative. The work done is negative, if that makes sense. I'm not sure I said it perfectly, but there is a minus sign relationship between work done and energy stored, potential energy stored. Okay, so this is just an old idea that you guys saw a long time ago. And again, here's that question of definite integration. What I really mean is u of b minus u of a equals integral from a to b of f ds cos theta. That's what I really mean. But assuming that potential energy is measured from a point of reference. So let's say we already know where the potential energy is zero. Maybe it's the surface of the earth, or maybe it's out at infinity at the edges of the universe. You do have one of these being zero in all cases. So usually they don't include on the left side a difference at all. They'll just say, hey, look, you can think of the potential energy as a scalar function. Okay, in our situations, right, we're pretty much always dealing with radial stuff, if you've noticed that. So for like a point charge, and I already did this calculation on the board, and let's just say it's positively charged, the E field is kq over r squared, and it's directed in the direction r hat. So which direction does the E field point? Radially away from the point. And therefore you put an r hat on there. So if you plug that into this formula and you sort of use the idea of potential energy right here in the world of the conservative electrostatic force, you end up with kq over r squared dr r hat dot r hat. In other words, dr is dr r hat, and F is, I forgot my extra field, I forgot my extra Q on top, sorry. Remember, you have two Q's on the top for the, you have two Q's on top for the force. I was doing field, I meant to write force. We're integrating force, aren't we? So my point is we have a K, Q, Q over R squared, R hat, and then there's a dr R hat. The two R hats dot to make the unit vector 1, 0, or just magnitude 1, I mean. And you just end up with negative K, Q1, Q2 over R squared dr. Then you just do an antiderivative. You get a minus R to the minus 1 instead of a R to the minus 2. So it ends up being K, Q1, Q2 over R. This is the potential energy function near a point charge. Potential energy function near a point charge. Okay? All right, so we're assuming that as r goes to infinity, u goes to 0. So I'm not doing a definite integral. There's already one point well defined and it happens to be a 0. So notice this is a scalar. That's very important. And you might say, why are you studying potential energy, Mr. Story? This lesson says electric potential. It doesn't say potential energy. You're right. All of this can be redone. Instead of integrating force to get potential energy, we can integrate field to get potential. So we'll do this again here in a minute, or at least talk about it. All right, so let's clear the ink here and move down. Oh, there's no button for that. Okay, that's fine. I didn't see a clear ink button. All right, so the scalars are easier to work with, right? Okay, recall that the results of scalar function, recall that though electric force involves both charges, Q1 and Q2, we actually defined the field. Remember when we first defined field, we said, let's pretend there is no victim charge, right? So nothing experiences force, but you can still sort of experience field when you're near a charged object. So we call that independent of the test charge. So our book calls it a test charge. If you don't have a test charge, you only have a source. You don't have something feeling force, but you can still feel the field, I suppose. Okay, so the electric field, remember, was the same thing as force, but it's missing that top Q1. So recall the units were newtons per coulomb. In the same way that we integrated force to get potential energy a long time ago in classical mechanics, we can also integrate field to get an antiderivative, and we call that electric potential. So we got U by integrating F, is what I'm saying. F dot ds. We're going to get V by integrating E. Very similar idea. Okay, so it's just going to come out, for a source charge, it's just going to come out to the same thing we had a second ago, but it will not have that top Q2 because the definition of field doesn't require it. Okay, it's not a vector, so I'm not going to put a direction on it. Now the SI unit is a volt, but really, if you think about it, we just integrated E, which is newtons per coulomb, times distance. So it's really just a Newton meter per coulomb. And you might recognize Newton meter. You've seen it twice before. It's a torque unit, but that's in the world of vectors. And it's also the joule. Sound familiar? A joule per coulomb. Which is a hint, because that would imply that it's related directly to energy, and it is. Okay, let's scroll down again. Can I erase? I found my clear ink button. I'm dying to push it. Okay, that was fun. Let's go now to a summary of these four quantities. So force for a point charge, this is for a point charge, so thank you for clarifying that earlier. Force is F equals, and it was K Q1 Q2 over R squared R hat. It's a vector. Potential energy is its scalar antiderivative. And we had KQ1 over R, and it's scalar, and we call that U, and I think there's a negative from the antiderivative. This assumes that U is going to 0 when R goes to infinity, so you can treat it as a definite integral of the improper form that we learned in Calc BC. Now, field, very similar, just think of it by analogy. E is KQ1 over R squared R hat, and the antiderivative of that would be negative KQ1 over R, and it's a scalar. So I'm not sure why, but on my original, I had an extra negative. I don't know how I got a positive potential energy earlier. Maybe I was going the wrong direction. But these should differ by negative, always. F should differ from U by negative, and E should differ from V by negative. And I forgot to leave the Q2 here from the antiderivative. Thank you. That's more or less a copier. I was also thinking ahead about what our potential function would look like. So notice that force and potential energy, if you're going to use those words, you need to have a victim and a source. So the first two in red, you need to have a victim and a source. You cannot possibly have potential energy of an object. You can have potential energy of two objects. Okay? That's important. But when you talk about potential in general, you expect to hear about one source, Q1. And that's important distinction there. Okay, notice that the field and the potential energy, I just said this, require two charges to exist because they're properties of a system of charges, and the field and the potential only require one charge to exist. That means they're there with or without a victim to experience them. You don't need a test charge to talk about fields and potentials. So the potential energy of a system is technically defined as the opposite of the work. So I wrote this earlier, but U is typically the opposite of W. Okay, you should have learned that actually a long time ago, but I don't think we need to get too into it. I never quite say it right when I get into it. So this is true in general, and W done by the electric field as we bring the particle in from infinity to some arbitrary point is going to give us these formulas without their left side looking like a delta. So I'm not going to use delta U or delta V. Some would say it's kind of redundant to do that. The only exception, the only time I'll use a delta is when I'm actually integrating from R equals 5 to R equals 7. Then I will write maybe a delta kind of thing. Okay. Because I'm not considering infinity at that point. At that point in time. Okay, so for a point charge at least, you can see there is actually a really simple relationship between U and V. So we just found the relationship between E and V, right? We found the relationship, some of this got erased, between F and U, but we never actually found a relationship between U and V. But look at them. Look at the relationship between U and V. It's a simple direct proportion in Q2. So if you times V by Q2, you get U, don't you? All right. So what I'm saying is you could think of V as, I think I'm filling in the wrong blank. Some of this stuff got really messed up. This was two charges, one charge. Potential energy is technically defined as the opposite of the work. Yeah, I wrote that in there already. Okay. And I thought I left these as blank, but they're already filled in for you. Sorry about that. We define potential V as U divided by Q. Speaking of U divided by the victim charge. So it's U divided by Q2. And SI units, therefore, are joules per coulomb. So you can see it right there staring you in the face. Potential energy on top, joules. Test charge on the bottom, coulombs. And we call that a volt. Now this means that since, remember the E field was newtons per coulomb. Remember E was measured in newtons per coulomb. You could technically times top and bottom by meters real quick. And then write the top as joules. per coulomb meters, and then you could cluster the joules per coulomb as a V. So some people actually say volts per meter when they're talking about E field. I know we're not talking about E field today, but this is something I wanted to throw in there because I don't know if you were watching when we did that little demonstration on the website. We were dragging the little charges around, and it was like just telling us the E field everywhere. It kept saying volts per meter, volts per meter. And I think it was you that was saying, well, I thought we measured it in newtons per coulomb. Same thing. Okay, so I just showed you that a newton per coulomb is a volt per meter. So anyway, now we have another way to talk about field if we ever want to. But voltage divided by distance typically gives us, voltage divided by distance gives us the idea, the intuitive idea of field. But the correct relationship is you differentiate voltage with respect to distance. If you remember my mountain drawings earlier. Okay, you'd be surprised how much of this you can handle without understanding it, actually. You can do quite a few problems without 100% grasping it. And that's okay for your first time through it, you know. All right, let's fill in a couple more blanks, and we'll call it a day. When a charge then is moved through a potential delta V, the potential energy in that system changes by the amount Q delta V. Make sure I'm filling this in correctly. Yeah. And when a particle moves from V initial to V final, the path taken doesn't matter. Does not matter. Because the electrical force is a conservative force. So that just means, you know, if you take let's say you take a spring. This is the best example I can think of. You take a spring, right? And you compress it. It doesn't matter if you compress it totally horizontally or if you kind of bend the spring this way first and then push it in and then relax it back to its original state. If your overall compression is, 1 inch and you compress that spring by 1 inch, it doesn't matter how wiggly the path was while compressing. If you end up with a before and an after picture like this, where it's before 4-inch spring, after 3-inch spring, you've got the same amount of potential energy stored either way. So you might compress it directly straight across, or you might like stretch it 1,000 times and then compress it 1 inch. Doesn't matter. As long as it's a 1-inch compression, in the end, you have the same amount of energy stored, right? Okay, that's what I was talking about in that last paragraph. Recall that in the case of one conservative force, the total mechanical energy is conserved. In other words, the initial potentials and kinetics add up to the final potentials and kinetics. If you want to, you could write that as K final minus K initial equals U final minus U initial. In other words, delta K is the opposite of delta U. I meant to write it this way. K final minus K initial equals U initial minus U final. In other words, delta K is the opposite of delta K, or if you want to, delta K is opposite of Q delta V. So that was 2 paragraphs to say a simple thing. If the potential change is Q delta V, then the kinetic change is the opposite, right? Because if you change the kinetic energy by 4 joules, you change the potential energy by 4 joules in the opposite way, if that makes sense. Because conservative forces are like that. Every time you lose potential, you gain the exact same amount of kinetic and vice versa. So you change it by Q delta V, the kinetic energy changes by negative Q delta V. Okay. If there's any other forces acting, then you're going to have to add in those as well. So if it's just electrostatical stuff, right, you can kind of bank on this rule. But if you're also going to throw in gravity and other things, you need to add another W. Or if somebody's going to actually grab the particle and push on it, not using electrostatic force, but just kind of pushing on it or pulling on it or whatever, you have to, of course, include that too. Whatever work done there will provide new energies as well to the system. So that's for outside stuff coming in. And we're real close to the end of the period. Wow. Is mine already filled in? Why don't you guys just take a moment and fill yours in? Does yours look like this or is it empty? Oh, okay. Is it too small? Do you want me to post it on the internet just in case? Mr. Shore will put it on Google Classroom today. I made all of this using that little add-on. this is nice because if you know F and you need V, here's your little formula down here. If you know E and you need V, here's your formula over here. Watch those negatives. Anytime you hop from a function to its antiderivative, a negative pops up. Or when you hop from a function to its derivative. Also, watch those little hats. They're only on field and force. Nowhere else. Only on field and force. Anything that's not field or force has a dot product, which is scalar, or simply no hats at all.